The oldest photograph in existence shows the universe at its birth. This faint glow is the cosmic microwave background, a celestial baby picture holding secrets we are only beginning to crack. For decades, we saw it as a simple snapshot, but it is really a dynamic map, its subtle patterns whispering of invisible forces that shaped everything. By the end of this journey, you will understand how dark energy, dark matter, and echoes from before the Big Bang are encoded in this ancient light. We will follow the trail from its accidental discovery to the high-tech telescopes hunting for its deepest truths. What if the key to the cosmos has been shining down on us all along? That faint hiss of static picked up by two radio astronomers was far more than a nuisance. Arno Penzias and Robert Wilson were troubleshooting their enormous horn antenna in New Jersey, baffled by a persistent microwave signal that seemed to come from every direction in the sky. They scrubbed away what they called a white dielectric material, evicting a pair of pigeons they thought were causing the problem, but the signal remained, a ghostly whisper permeating all of space. They had accidentally stumbled upon the afterglow of creation itself, the cooled and stretched remnants of the universe's first light. This discovery of the cosmic microwave background was the smoking gun for the Big Bang, confirming the universe had a hot, dense beginning. Yet this profound revelation came with a deep mystery. The glow was almost perfectly smooth, the same temperature in every direction. A universe born from a violent explosion should be lumpy, filled with wild variations in temperature and density. How could something so chaotic produce a result so incredibly uniform? This cosmic perfection was paradoxically a problem. It pointed toward a missing chapter in the universe's story, a brief and spectacular event that stretched the fabric of space itself to silken smoothness, an event we call inflation. That cosmic perfection, that impossibly smooth baby picture of the universe, demanded a radical explanation. The answer lies in a concept so powerful it redefines the very meaning of rapid, an event known as cosmic inflation. To understand it, picture a balloon covered in microscopic, random wrinkles. Now, blow that balloon up to the size of the entire Earth. Those tiny, insignificant wrinkles would be stretched into vast, gentle undulations across the globe. Cosmic inflation proposes that our universe did exactly this in its first fleeting fraction of a second, expanding faster than the speed of light itself. This solves the Great Horizon mystery. How could regions of space now billions of light-years apart, regions that could never have communicated with each other, possibly have the same temperature? Inflation explains it by revealing they were once intimately connected. A tiny patch of the primordial cosmos stretched to an unimaginable scale, ironing out all the wild variations into a nearly perfect smoothness. But that smoothness is not quite perfect, and that is where the magic happens. The subtle temperature variations we see in the cosmic microwave background, those tiny hot and cold spots, are the magnified quantum fluctuations from that inflationary burst. In the furious expansion of space-time, the faintest whisper of randomness, a quantum fizz at the smallest possible scale, was stretched into the largest structures we see. These ripples in the fabric of reality became the gravitational seeds for everything to come. Every galaxy, every star, every planet, and us. We all grew from those infinitesimal wrinkles imprinted during the universe's first moment. This entire cosmic history was driven by an unseen force, often imagined as an inflattened field, a kind of energy that powered this spectacular growth spurt and then faded away, leaving its signature etched into the ancient light. The patterns we detect in the CMB's polarization, the specific way this light vibrates, are a direct prediction of this theory, making this afterglow a time machine to the universe's violent birth. What other profound signatures did this explosive beginning leave behind, waiting in the static for us to decode? Those subtle ripples in the cosmic background are not just a fossil of the past. They are a living imprint, a canvas warped by an unseen artist. The same gravitational seeds that grew into galaxies also left a second, more ghostly signature on the ancient light. Think of the early universe as a vast hot pond. The cosmic microwave background is the surface of that pond, frozen in time. The temperature variations are the ripples. But something massive was moving beneath the surface, its invisible presence bending the path of the light. That something is dark matter. This mysterious substance does not interact with light at all. It neither glows nor casts a shadow in the conventional sense, yet it possesses mass, and with mass comes gravity. As the primordial photons of the CMB began their epic journey across the cosmos, they did not travel in perfectly straight lines. They passed through the evolving gravitational landscape, a terrain increasingly dominated by clumps of dark matter. These invisible concentrations acted like lenses in space, subtly redirecting the light and distorting the pattern of the ripples we observe today. It is a phenomenon called gravitational lensing. By meticulously analyzing these minute distortions, scientists perform a kind of cosmic cartography. They can map where the light was bent, and from that, they can reconstruct the location and distribution of the invisible mass that caused the bending. The result is a ghost map of the universe, a detailed chart of the dark matter scaffolding upon which the galaxies are hung. This is not just theoretical. It is direct, physical evidence that dark matter is real, a tangible substance that shaped the cosmic web and left its fingerprints on the very first light. Its ghostly hand guided the formation of everything we see. But if dark matter provides the gravitational backbone for the cosmos, what force is working against it, pushing the universe apart? But if dark matter is the gravitational anchor holding the cosmic structure together, then the universe holds a far stranger secret, a force working in direct opposition. The expansion of the cosmos is not slowing down, as you might expect from the relentless pull of gravity. It is speeding up. Imagine you throw a ball into the air, and instead of slowing as it rises, it suddenly rockets away from you faster and faster. This is the baffling reality of our universe, driven by a mysterious push we call dark energy. While its most dramatic effects are seen in the relatively recent cosmos, its ghostly signature is also etched into the ancient light of the cosmic microwave background. How can a snapshot from the infant universe tell us about this modern acceleration? The CMB acts as a cosmic starting gun. Its precise pattern of hot and cold spots reveals the universe's initial geometry and the total amount of matter and energy present at that early time. We learn from it that the overall geometry of the cosmos is flat, like a vast, endless sheet. When scientists add up all the ordinary matter and dark matter we can detect, there is a huge portion of the cosmic pie missing. The universe's flat geometry demands a specific density, and matter alone does not account for it. That enormous gap, that missing ingredient, is dark energy. It is not just a small component. It is the dominant force in the universe, making up the vast majority of everything that exists. It appears to be an intrinsic property of empty space itself, a kind of repulsive gravity woven into the very fabric of spacetime, causing the cosmos to fly apart at an ever-increasing rate. By giving us this pristine starting point, the CMB allows us to run the cosmic film forward. We can track how, for billions of years, gravity's tug-of-war was dominant, slowly building galaxies and clusters. But then, as the universe grew larger and emptier, dark energy's constant push began to overwhelm the pull of matter. It took over the cosmic expansion, setting the universe on its current course of accelerated flight. This revelation forces a profound question. Is dark energy a true constant, an unchanging force of nature, or is it something more dynamic, an energy that itself evolves over time, holding the ultimate key to the final fate of all we see? The faint temperature variations in the cosmic background are a meticulous script written in the language of the early universe. These anisotropies, tiny differences of just 1 part in 100,000, are far from random static. They form a complex, structured pattern, a cosmic codebook waiting to be read. To decipher it, scientists use a powerful mathematical technique known as power spectrum analysis. Think of it as listening to a complex chord of music and separating it into its individual notes, each with a specific pitch and volume. This analysis breaks down the sky into fluctuations of different angular sizes, from broad swaths to fine details, and plots their relative strength. The resulting graph is not a smooth line. It is a dramatic landscape of peaks and valleys, each one a precise measurement of the universe's fundamental properties. The first and tallest peak tells us the overall geometry of the cosmos is flat, like a vast, endless plane. The second peak, and particularly its relationship to the first, acts as a cosmic scale, weighing the total amount of ordinary atomic matter, the stuff of stars and planets and us. The third peak reveals the hidden hand of dark matter, its height betraying the density of this invisible gravitational glue. Every wiggle in this spectrum is a direct echo from a time just 380,000 years after the Big Bang, a fossilized record of the pressure waves that sloshed through the primordial plasma. By reading this codebook, we can take a complete census of the cosmos, quantifying its ingredients with stunning accuracy and confirming our standard model of cosmology. Yet this detailed temperature map is only half of the message carried by this ancient light. The very way it vibrates, its polarization, contains a whisper from a time even closer to the very beginning of everything. The temperature map of the cosmic background is only the beginning of the story. To read the deepest secrets, we must also see how this ancient light vibrates. Every wave of this primordial glow has a specific orientation, a property known as polarization. This polarization acts like a compass, pointing back to the forces that last scattered the light. Scientists categorize these patterns into 2 distinct types, E modes and B modes. E modes are relatively straightforward, generated by the simple density fluctuations of ordinary matter and dark matter, creating patterns that look like radial lines or concentric circles. They are the expected fingerprint of the universe's basic structure, but the B modes are something else entirely. These are curling, swirly patterns, the kind that could only be created by a twisting force, a literal shaking of the fabric of reality. The holy grail of this entire field is the detection of primordial B modes. These would be the direct signature of gravitational waves generated in the first infinitesimal moment of cosmic inflation. Think of the infant universe as a vast bell. The violent event of inflation would have struck that bell, sending powerful ripples through the very structure of space-time itself. These gravitational waves then traveled through the hot, dense plasma, shaking it and imprinting a unique, twisting pattern onto the polarization of the light just as it was being set free. Finding this faint swirl in the cosmic static would be like finding the fossilized ripples from that first cosmic bell ring. It would be our most direct evidence that inflation truly happened, and it would open a window into an energy scale 1 trillion times higher than anything we can create in particle colliders. This is the frontier. The signal is incredibly faint, drowned out by the glare of interstellar dust in our own galaxy and other astrophysical foregrounds. The hunt for this whisper demands telescopes of breathtaking sensitivity placed at the most remote locations on Earth, at the South Pole or high in the Chilean deserts, where the atmosphere is thin and stable. It is a painstaking process that pushes the limits of our technology and our patience, a cosmic treasure hunt where the prize is a glimpse of the quantum gravity that ruled the universe's very first instant. Beyond the glow of photons lies an even more elusive background, a sea of cosmic ghosts. These are neutrinos, trillions of which are streaming through your body at this very moment, a relic from the universe's first second of existence. While the cosmic microwave background photons were set free after 380,000 years, this cosmic neutrino background decoupled when the cosmos was barely a second old. These particles are so ethereal they pass through entire planets as if they were empty space, making them nearly impossible to trap and observe directly. Yet, despite their ghostly nature, they left a permanent scar on the cosmos we can measure today. Their influence is written into the very patterns of the CMB. In the primordial plasma, these neutrinos were ultra-high energy, moving at almost the speed of light. This incredible velocity gave them a unique property. They acted like a cosmic fluid that could not easily be compressed. As gravity tried to pull ordinary matter into the tiny seeds that would become galaxies, this sea of fast-moving neutrinos effectively washed out the smallest ripples. They smoothed over the finest details of the cosmic blueprint. We see this effect clearly in the power spectrum of the CMB, the same graph of peaks and valleys that reveals so much. The presence of this neutrino background subtly suppresses the power in the smaller scale fluctuations. It is a specific, telltale signature of an invisible component gently holding back the growth of the smallest structures. By measuring this suppression with extreme precision, cosmologists have not only confirmed the existence of this background, but have also counted the number of neutrino families and placed limits on their tiny masses. This is a profound achievement, using the ancient light of the CMB as a sensor to detect a particle background we can never hope to see with a telescope. It reveals a universe layered with fossils, each from a different, more ancient epoch. If the CMB is a baby picture, the cosmic neutrino background is an ultrasound from the universe's first breath. And the hunt for even earlier relics continues, pushing back toward the moment of creation itself, searching for imprints from a time before time had any real meaning. Yet even as we decode these subtle whispers, a far larger and more disturbing pattern has emerged from the data, one that seems to defy the very foundation of modern cosmology. This is the mystery known as the axis of evil. According to our most cherished principles, the universe should have no center and no edge. It should look on the largest scales the same in every direction, a concept called statistical isotropy. The cosmic microwave background should resemble a vast, random static, with hot and cold spots scattered without any preferred alignment. But when scientists created the most detailed full sky maps, they found something startling. The largest fluctuations in the CMB are not entirely random. They appear to be subtly aligned along a particular axis, a kind of cosmic spine running through the universe. Even more strangely, this so-called axis of evil seems to be correlated with the plane of our own solar system. This is profoundly unsettling. It is as if you drew a map of the entire world and discovered that all the mountain ranges were mysteriously aligned with the street you live on. The implication is staggering. It suggests a preferred direction in the cosmos, a fundamental lopsidedness that our standard model of the universe simply does not allow. So what could it be? The most conservative explanation is a statistical fluke, a cosmic mirage created by the way we filter the data, or perhaps an unaccounted-for foreground effect from our own galactic neighborhood. But the signal has persisted through multiple satellite missions, refusing to vanish. This has led to more radical proposals. Could it be a fossil from a time before the Big Bang, an imprint from a previous cosmic cycle that set a primordial spin on our universe? Or does it hint that the shape of space itself is far more complex than we imagine, perhaps folded into a vast, repeating structure that creates this apparent alignment? This anomaly forces a humbling realization. Our fantastically successful model of the cosmos, which explains so much with such precision, might be incomplete. The CMB is not just confirming our theories, it is actively challenging them, presenting us with a puzzle that cuts to the core of our understanding of reality. What if the universe is trying to tell us that we are missing something fundamental, a hidden variable that rewrites the first page of the cosmic story? Another profound mystery is written in the cold. Scattered across the cosmic microwave background are regions of slight temperature variation, but one area stands out dramatically, a vast patch of sky that is significantly colder than the rest. Astronomers call it the cold spot. This isn't just a minor statistical blip, it is a colossal cosmic chill, a region so large and so cold that it defies easy explanation within our standard model of the universe. It is as if you were looking at a detailed thermal map of the Earth and found a continent-sized area that was 20 degrees colder than everything around it for no apparent reason. The most straightforward explanation points to a cosmic emptiness. Imagine a CMB photon, a particle of that ancient light, traveling for 13.8 billion years to reach our telescopes. On its long journey, if it passes through a truly enormous region of space that is mostly empty, a cosmic supervoid with far fewer galaxies and less dark matter than average, something peculiar happens. As the photon enters this vast underdensity, it must climb out of a gravitational well, but because the universe is expanding and dark energy is at work, the well itself is becoming shallower as the photon traverses it. The photon loses energy in this process, and a loss of energy for light means a shift to a colder temperature. This is known as the integrated Sachs-Wolfe effect. It is a direct, detectable result of dark energy's influence on the cosmic landscape. The problem is, when astronomers search the direction of the cold spot for a void large enough to cause such a profound cooling, they come up short. The underdense regions we can find are simply not vast enough to account for the signal we see. It is like having a massive shadow cast on a wall, but finding only a small object in front of the light source. This discrepancy has forced scientists to consider far more exotic possibilities. What if the cold spot is not a lack of something, but the presence of something strange? One compelling theory suggests it could be a cosmic texture. This is not a wrinkle in space, but a knot. In the incredibly hot, early universe, as the fundamental forces of nature were separating from a single, unified force, phase transitions occurred, much like water freezing into ice. Sometimes these transitions could happen imperfectly, creating defects in the very fabric of space-time. A texture is one such defect, a tangled, energetic knot in the fields that define reality. If a texture formed and then unraveled in the path between us and the CMB, the immense energy involved could have imprinted that specific, large cold spot onto the primordial light. Finding evidence for a texture would be a monumental discovery. It would provide a direct, observational window into physics at energy scales trillions of times beyond what our particle colliders can reach, offering a tangible clue to the grand unification of all forces. The cold spot, therefore, remains a cosmic Rorschach test. Is it the shadow of a colossal nothing, a fingerprint of dark energy, or is it the scar of a primordial defect, a frozen snapshot of a cosmic symmetry breaking in the first moments of time? This single anomaly pushes at the boundaries of our knowledge, reminding us that the oldest light in the universe still holds profound and unsettling secrets. This ancient light does more than just reveal the past, it actively illuminates the present. The cosmic microwave background serves as a perfect cosmic backlight, shining through everything that formed after it. When this primordial radiation encounters a massive galaxy cluster on its journey to us, something remarkable happens. The space between the galaxies in these clusters is not empty. It is filled with a superheated gas, a plasma of incredibly energetic electrons. As the faint photons of the CMB pass through this seething ocean of particles, they collide with these high-speed electrons. In these collisions, the photons get a boost of energy, a kick that changes their very nature. This process is known as the Sunyaev-Zeldovich Effect. It leaves a unique fingerprint, a specific distortion in the CMB's spectrum right at the location of the galaxy cluster. Instead of a cold spot, we see a slight shadow, a specific spectral signature that betrays the presence of that immense structure. The true power of this effect lies in its independence from distance. For most astronomical objects, the farther away they are, the fainter they appear. But the Sunyaev-Zeldovich distortion does not dim with cosmic expansion. Whether a cluster is relatively nearby or at the edge of the observable universe, the magnitude of the distortion it imprints on the CMB remains just as detectable. This makes it an unparalleled tool for taking a census of the most massive objects in the cosmos. By scanning the CMB for these subtle spectral shadows, astronomers have compiled catalogs of thousands of previously unknown galaxy clusters. This is not just about making a list. Each cluster detected in this way is a data point in the grand story of cosmic evolution. The number and distribution of these clusters across cosmic time tell us how the large-scale structure of the universe, the cosmic web of filaments and nodes, has assembled over billions of years. They test our models of dark matter and dark energy, as these invisible components control the growth rate of these colossal formations. Furthermore, the effect allows us to study the properties of the intracluster plasma itself, that scorching gas which contains more ordinary matter than all the stars in all the galaxies within the cluster. By analyzing the distortion, we can measure the gas's temperature and pressure, understanding how these vast reservoirs of matter behave. The CMB, the oldest picture we have, thus becomes a dynamic tool. It is a backlight that reveals the silhouette of the universe's contemporary architecture, proving that the first light is still actively helping us map the cosmos. The universe did not remain a dark, neutral sea forever. After 400 million years of profound darkness, a new dawn began to break. This was the Epoch of Reionization, a cosmic revolution that forever changed the character of the cosmos. The first stars and galaxies ignited, and their brilliant, furious light began to flood the emptiness. This was not the gentle starlight we know today. These were colossal, short-lived behemoths, pouring out intense ultraviolet radiation. This energetic light acted like a cosmic blowtorch, slamming into the vast clouds of neutral hydrogen gas that filled the universe. One by one, the radiation ripped electrons away from their atomic nuclei, transforming the transparent neutral hydrogen into a diffuse, glowing plasma of free electrons and protons. The universe was being fundamentally altered, reionized from the ground up. This great transformation left its own distinct fingerprint on the ancient light traveling through it. As the photons of the cosmic microwave background continued their journey, they now had to pass through this newly ionized intergalactic medium. Many of these ancient photons were rescattered by the free electrons, a final interaction that imprinted a specific, large-scale pattern onto the light's polarization. This is the E-mode polarization we detect today, a vast, gentle swirl across the sky that tells the story of this second dawn. By measuring the precise character of this polarization signal, cosmologists can perform a kind of cosmic archaeology. They can determine when reionization began, how long it lasted, and how quickly the first luminous objects lit up the cosmic dark ages. This signal bridges an immense gap in our understanding, connecting the smooth, primordial universe revealed by the CMB to the structured, galaxy-filled cosmos we inhabit. The ancient afterglow carries within it the ghostly echo of the very first starlight, a permanent record of the moment the universe woke up and began to build the world we know. But our most precise cosmic map may contain a fundamental crack. This is the Hubble tension, a stubborn discrepancy that threatens to unravel our standard model of the cosmos. The problem lies in the universe's current expansion rate, a number known as the Hubble constant. We have two primary ways to measure this speed. The first uses the cosmic microwave background. By reading the detailed pattern of the CMB, we can determine the universe's initial conditions, its ingredients and geometry. We then run the cosmic film forward using our best model of physics, calculating what the expansion rate should be today. It is a pristine, early universe measurement projected across 13.8 billion years. The second method is more direct. Astronomers use so-called cosmic distance ladders, like pulsating stars called Cepheid variables and brilliant stellar explosions known as Type Ia supernova, to measure the expansion rate in our own cosmic neighborhood. These are like mile markers on a highway, allowing us to clock the universe's speed right now. The tension is this: the local, direct measurements consistently return a faster, more rapid expansion rate than the value extrapolated from the ancient CMB. It is as if you calculated how fast a car should be going based on its acceleration out of the gate, but when you looked at your speedometer today, it showed a significantly higher number. The difference is not large, but it is persistent and has withstood intense scrutiny. This is not just a minor statistical fluke. It is a glaring inconsistency that has grown stronger with each new, more precise observation. So what could be causing this rift in our cosmic data? The simplest explanation is an unaccounted-for systematic error, a subtle miscalibration in one of the measurement techniques that has eluded detection. Yet, as both methods are refined and the discrepancy remains, the possibility grows that we are seeing a genuine sign of new physics. Perhaps dark energy is not the simple, constant force we assume it to be. What if its strength has been increasing over time, giving the cosmic expansion an extra, unexpected push that our model does not include? Or maybe the early universe contained an additional, unknown type of radiation, like a new species of neutrino, that subtly altered the rate at which structures formed, throwing off our backward calculations from the CMB. The CMB sits at the very heart of this mystery. It is the bedrock upon which our early universe model is built, and now it is the source of our greatest confusion. The Hubble tension is a cosmic wake-up call, a clear signal that our understanding of the universe, for all its successes, might be missing a crucial piece. This ancient light is not just confirming our theories, it is actively challenging us to find a deeper truth. Magnetic fields are the silent, invisible architecture of the cosmos, threading through planets, stars, and the immense voids between galaxies. Their universal presence poses a profound puzzle. Where did they come from? The conventional story suggests they were forged later, spun into existence by the turbulent dynamos of early stars and galaxies. But what if these fields are far more ancient, a primordial feature woven into the fabric of space-time at its birth? This idea, known as primordial magnetogenesis, suggests magnetic fields were generated in the universe's first instance during the violent epoch of inflation, or the subsequent phase transitions as the fundamental forces split apart. If true, these infant magnetic fields would have been stretched to cosmic proportions, imprinting their presence on the universe's first light. A universe laced with such primordial magnetism would have created a turbulent plasma. As the particles of the cosmic microwave background traveled through this magnetized medium, their journey would have been subtly altered. The fields would have affected how the photons propagated, inducing specific telltale signatures. They would have generated unique patterns in the light's polarization, contributing to the swirling B-modes we so desperately hunt for, and they would have left distinct distortions in the temperature power spectrum, the very graph of peaks and valleys that serves as our cosmic codebook. So far, our most sensitive telescopes have not found this clear signal. Current CMB data places incredibly tight constraints, telling us that if a primordial magnetic field exists, it must be exceedingly weak. Yet the hunt is far from over. Each new experiment pushes the limits of detection, scanning the faint static for that elusive magnetic whisper. Finding it would be a revolution. It would mean that magnetism is not merely a later byproduct of cosmic structure, but a fundamental character in the universe's story, present from the very first moments. Such a discovery would open a direct window into physics at energies trillions of times beyond the reach of any particle collider, revealing the turbulent, magnetized dawn of everything we see. The smoothness that inflation gave our universe might be its most deceptive feature. This theory of a single, explosive beginning naturally spirals into a far grander and more chaotic vision, a concept known as the multiverse. The mechanism that flattened our cosmic neighborhood may not have been a one-time event. Instead, it could be an endless, self-replicating process called eternal inflation. Picture a vast, bubbling cauldron of space-time, forever expanding at an unimaginable rate. Within this frothing medium, random quantum fluctuations can trigger localized drops in energy, causing pockets of this hyper-expansion to slow down and settle. Each of these pockets becomes a stable bubble universe, nucleating within the eternally inflating background like a soap bubble forming in a turbulent foam. Our entire observable cosmos, with its hundreds of billions of galaxies, could be just one such bubble. The staggering implication is that other bubbles, other universes, could be constantly popping into existence, each with its own unique properties. The fundamental constants we take for granted, the strength of gravity, the mass of an electron, even the number of spatial dimensions, might not be universal laws at all. They could be mere local bylaws, the random outcome of how our particular bubble formed and cooled. In this infinite cosmic ensemble, every conceivable set of physical rules would be realized somewhere. While the very nature of these other universes places them forever beyond our direct observation, the afterglow of our own birth might hold tantalizing, indirect clues. The mysterious cold spot, that vast and inexplicably cold patch in the cosmic microwave background, has been proposed as one such ghostly bruise. Could it be the circular imprint of a collision, the place where our budding bubble universe long ago brushed against another in the crowded multiversal foam? Such a cosmic fender bender would have transferred immense energy, leaving a distinct signature in the ancient light. Beyond specific anomalies, the very statistical character of the fluctuations we see in the CMB, the specific arrangement of its hot and cold spots, could be used as a probe. These patterns are a direct output of the inflationary energy field that birthed us. By decoding them with exquisite precision, we might infer the shape of that field, the landscape of possible vacua predicted by theories like string theory. This transforms the cosmic microwave background from a simple baby picture into something far more profound. It becomes a potential portal, a single window looking out from our isolated bubble onto the contours of a reality so vast and strange that our universe is merely a single grain of sand on an infinite shore. These new observatories are not merely upgrades. They represent a quantum leap in our ability to perceive the subtle textures of the ancient universe. On the high, dry plateaus of the Atacama Desert in Chile, projects like the Simons Observatory and its planned successor, CMB-S4, are rising to the challenge. These facilities will be equipped with arrays of hundreds of thousands of superconducting detectors, each chilled to a fraction of a degree above absolute zero. This vast army of electronic eyes will scan the sky with a collective sensitivity that dwarfs all previous efforts combined. Their primary mission is to map the faint polarization of the cosmic microwave background with a clarity we have never before achieved, hunting for the elusive swirl of primordial B-modes with the tenacity of a detective searching for a single, faded fingerprint on a continent. But their ambition does not stop there. The sheer volume of data will allow for a cosmic neutrino weigh-in. By measuring with exquisite precision how the CMB fluctuations are suppressed on small scales, these telescopes could finally pin down the total mass of all neutrino species, a fundamental unknown in particle physics. They will also trace the invisible web of dark matter with unprecedented resolution, charting its gravitational lensing effects in such fine detail that we could map the distribution of this mysterious substance across vast swaths of the cosmos. Simultaneously, a different approach will unfold in the vacuum of space. The LIGHT-BIRD mission, a satellite observatory, is designed to conduct a full sky survey entirely free from the shimmering interference of Earth's atmosphere. Its pristine view will provide the cleanest possible search for the largest scale B-mode patterns, the specific signal that could confirm cosmic inflation. Together, these ground-based and space-based efforts form a comprehensive strategy to interrogate the first light. They will listen for any faint, anomalous hum in the CMB spectrum, a sign of immense energy injections from exotic events in the universe's first seconds, perhaps from the decay of unknown particles or the evaporation of primordial black holes. This is an observational arms race, a global endeavor to push our measurements to their ultimate limits. The data that flows from these instruments will either solidify our standard model of cosmology into an unshakable edifice, or it will finally reveal the crack that forces a revolutionary new understanding of reality itself. This ancient glow, for all its staggering detail, marks a fundamental boundary to our vision. The cosmic microwave background is a two-dimensional photograph of the universe at the tender age of 380,000 years. We call this moment the surface of last scattering, the instant the fog cleared and light was set free, but that very clarity creates a profound barrier. We cannot see past this luminous wall. The era before this moment is a complete mystery, a cosmic dark age in the truest sense, where the universe was an opaque, seething plasma, trapping every photon almost instantly after it was born. This means the first 380,000 years of cosmic history are permanently veiled from our telescopes. The most violent and transformative events, the very birth cry of the Big Bang and the searing flash of inflation, are completely hidden behind this impenetrable curtain of primordial fire. Even if we could somehow rewind before this surface, we would confront an even deeper limit. The theory of inflation, which so elegantly explains the universe's smoothness, comes with a cosmic side effect, a kind of universal amnesia. The frantic, faster-than-light stretching of spacetime would have ironed out any pre-existing wrinkles, effectively erasing all information about what, if anything, came before. Quantum fluctuations it magnified were born in that violent expansion, overwriting any prior history like a new recording on an old tape. This leaves us staring at the CMB as the ultimate starting line. It is the initial condition for everything we can observe, but it offers no hints about its own origin. Why do these particular fluctuations exist? Why do the fundamental constants have the precise values that allow for galaxies, stars, and life? The CMB is silent on these ultimate questions. This is the cosmological information paradox, a reminder that our most powerful map of the cosmos is also a cage, defining the absolute limit of our empirical knowledge. To peer behind this veil, scientists must turn to indirect and creative methods. They search for the faint imprint of primordial gravitational waves in the CMB's polarization, ripples that could carry news from that hidden epoch. They use powerful particle colliders to recreate the insane energies of the universe's first moments, hoping to find clues in the behavior of matter itself. The CMB is the end of one story, the story of what we can see, but it is also the beginning of a much deeper mystery, the question of what lies forever beyond our view, in the timeless silence before the first light. This delicate balance, revealed so clearly in the cosmic codebook, points toward a staggering possibility. The fundamental numbers that govern our universe are not just arbitrary. They appear to be exquisitely fine-tuned for life. The precise density of matter and energy we measure from the CMB is a perfect example. If that number were even slightly higher, the gravitational pull would have been too strong. The entire universe would have reversed its expansion and collapsed back in on itself in a fiery big crunch long before stars or planets could ever form. Conversely, if that density were just a fraction lower, the cosmic expansion would have been too rapid, matter would have been spread too thin, and the gentle gravitational tugs that pulled gas together into galaxies, stars, and eventually us would have been powerless. The universe would be a dark, empty, and lifeless void. This cosmic tightrope walk is not an isolated case. The strength of gravity, the force that holds planets in orbit, is perfectly balanced against the explosive power of the Big Bang. If gravity were any stronger, stars would burn through their fuel in millions of years instead of billions, leaving no time for complex life to evolve on orbiting worlds. If the nuclear force that binds atomic nuclei were even a few % different, the elements essential for life, like carbon and oxygen, would never have been forged in stellar furnaces. We are left with a profound question. Why does this particular set of rules, so clearly imprinted on the ancient light of the CMB, allow for our existence? This line of thinking leads directly to the Anthropic Principle. In its simplest form, it states that the universe we observe must be compatible with the conscious life that has emerged to observe it. We could not possibly find ourselves in a universe that prohibits life, so the very fact that we are here to take this measurement places a selection effect on the kind of cosmos we see. For some, this fine-tuning suggests a purposeful design. For scientists exploring ideas like eternal inflation and the multiverse, it offers a different, perhaps even more mind-bending explanation. In an infinite multiverse where countless bubble universes are constantly budding into existence, each one is born with a random set of physical constants and laws. The vast, overwhelming majority of these universes would be stillborn or sterile, their parameters hopelessly wrong for complexity. But in a near-infinite array of possibilities, a tiny fraction of bubbles will, purely by chance, have the perfect Goldilocks conditions for life. We do not live in a special universe in this view. We simply live in one of the rare habitable ones. Our cosmic address is not privileged, it is just lucky. The cosmic microwave background thus becomes more than a historical record. It is a philosophical document, a piece of evidence that connects the cold, hard data of cosmology to the deepest questions of meaning and our place in the grand scheme of existence. The ancient light asks us not only how the universe works, but why this particular universe, against all apparent odds, is a home. The search for quantum gravity pushes our understanding of reality to its absolute limits. At this frontier, the cosmic microwave background becomes a testing ground for one of the most ambitious ideas in physics, string theory. This framework suggests that the fundamental particles of the universe are not tiny points, but unimaginably small, vibrating loops of energy. For the mathematics of this theory to work, these strings must vibrate in a reality with more than the three spatial dimensions we know. The extra dimensions are thought to be curled up or compactified on a scale trillions of times smaller than an atom. The sheer energy required to probe such scales is far beyond any particle collider we could ever build, but the universe itself was once such a collider. In its first fiery moments, the energies were immense enough to potentially excite these extra dimensions and leave a permanent scar on the cosmos. One potential relic is a cosmic string. Unlike ordinary strings, these are not the fundamental strings of the theory, but massive, filament-like defects in spacetime, immense cracks in reality left over from the early universe. As the cosmos expanded, these colossal, vibrating strings would have sliced through the primordial plasma, their immense gravitational influence creating sharp, line-like discontinuities in the temperature of the CMB. It would be like seeing the ghostly scratch of a cosmic fingernail across the oldest photograph. Furthermore, the presence of extra dimensions would fundamentally alter how gravity propagates. The primordial gravitational waves generated by inflation, the very ripples we hunt for in the B-mode polarization, would travel through a richer, more complex spacetime. This could leave a distinct imprint on the pattern of those swirls, a subtle deviation from the predictions of standard inflation that would point directly to the hidden architecture of reality. While no such definitive signature has yet been found, the CMB provides our only realistic chance to observe these effects. It is a bridge spanning the vastest cosmic scales and the tiniest quantum realms. A single, ancient dataset that might one day reveal the universe is not just stranger than we imagine, but is humming with the vibrations of unseen dimensions. This ancient light leads us to the precipice of the ultimate question. Why does anything exist at all? The cosmic microwave background does more than map the universe's infancy. It forces us to confront the very nature of existence and the puzzle of why there is something rather than nothing. Our standard Big Bang story is a magnificent tale of cosmic evolution, tracing everything back to a state of immense heat and density. But that story has a glaring hole. It describes the universe's explosive growth from that initial state, yet it offers no explanation for the singularity itself, that point of infinite density where the laws of physics as we know them simply break down. The theory of cosmic inflation provides a potential and deeply unsettling answer. It suggests our entire universe could have spontaneously emerged from a quantum fluctuation. Picture a state known as a false vacuum, an unstable form of nothingness brimming with latent energy. In this weird quantum realm, empty space is not truly empty. It fizzes with temporary particles popping in and out of existence, borrowing energy from the future in a constant, unpredictable dance. Inflation proposes that our cosmos began as one of these fleeting quantum jitters, a microscopic bubble in this false vacuum that, by pure chance, tunneled into a lower energy state. This transition released a colossal amount of energy, triggering the inflationary expansion that blew that quantum speck into our entire observable universe. The entire vast cosmos, with its hundreds of billions of galaxies, may be the magnified remnant of a subatomic event. This is where the CMB becomes our most profound evidence. Those subtle temperature variations, the hot and cold spots we meticulously map, are the direct descendants of those primordial quantum fluctuations. They are the original quantum fuzz, stretched to cosmic proportions by inflation and frozen into the sky for us to observe. The entire cosmic tapestry, from the grandest galaxy cluster to the smallest star, grew from these infinitesimal seeds. This perspective fundamentally shifts the question of creation. It moves the conversation from a theological first cause to a domain of quantum mechanics. The universe may not require a creator in the traditional sense. Instead, it could be a natural, if spectacular, consequence of the inherent unpredictability woven into the fabric of reality at its smallest scales. According to the strange rules of quantum physics, something can come from nothing because at that fundamental level, what we call nothing is never truly empty. It is a seething potentiality, a quantum foam from which entire universes can spontaneously bubble into being. The cosmic microwave background is the tangible proof of this genesis, a fossilized quantum event written across the entire sky, whispering that our entire reality might be the result of the ultimate cosmic coincidence. That iconic full sky map, with its mottled blue and red spots, has escaped the confines of scientific journals to become a modern cultural artifact. It is the baby picture of the universe, a phrase that has lodged itself in our collective consciousness. You find this image not just in textbooks, but in art installations where its patterns ripple across vast walls, in musical compositions that translate its temperature fluctuations into sound, and as a backdrop in films and television, symbolizing the ultimate frontier. This specific image makes the abstract, almost unimaginable concept of the Big Bang something we can see and hold in our minds. It grounds a 13.8 billion-year-old story in a single, tangible visual. More than just a map, it acts as a profound mirror. Every element that makes up our bodies, the Earth, and the stars was forged in the cosmic furnaces that only ignited because of the specific density variations, the very hot and cold spots imprinted on this light. We are not just looking at a distant past, we are looking at the blueprint for our own existence. This connection is fostered through planetarium, shows that project this ancient glow onto domed ceilings and documentaries that walk us through its discovery. These experiences democratize cosmology, transforming complex physics into a source of shared awe and wonder. Anyone, anywhere, can gaze upon this afterglow of creation and feel a sense of connection to the grand narrative of the cosmos. The cosmic microwave background has transcended its scientific data points to become a piece of our shared human heritage. It is a universal symbol of our insatiable curiosity, a permanent reminder etched across the sky of our humble yet profound place in a vast and evolving universe. The quest to capture the universe's first light demands more than just powerful telescopes. It pushes human ingenuity to its absolute limits, forcing the invention of technologies that then ripple out into the wider world. To detect the CMB's ghostly whisper, scientists had to build ears of unimaginable sensitivity. This led to the creation of revolutionary superconducting detectors, like transition edge sensors and microwave kinetic inductance detectors. These are not ordinary cameras. They are exquisitely tuned devices that must be cooled to within a fraction of a degree of absolute zero, the coldest temperature possible in the universe. At these deep cryogenic temperatures, the detectors become so sensitive they can register the tiny amount of heat deposited by a single photon of the ancient cosmic background. But building these instruments is only half the battle. The other half is making sense of the data. The signal from the CMB is buried under a mountain of foreground noise, from our own galaxy's radio glow to the faint emission of distant quasars. To isolate the true cosmic signal, cosmologists had to pioneer incredibly sophisticated algorithms for map-making and component separation. These are not simple filters. They are complex statistical engines that can tease apart overlapping signals, a process that has directly advanced the fields of machine learning and big data analytics. The practical benefits of this cosmic research are already here, woven into the fabric of daily life. The advanced cryogenic systems perfected for cooling CMB detectors are now essential for quantum computers, which require ultra-cold environments to function. The highly sensitive readout electronics developed for these telescopes have been adapted to improve the resolution of medical MRI machines, giving doctors a clearer view inside the human body. The same microwave detection technology is at the heart of the full-body scanners used in airport security, seeing not with light but with radio waves. This is the hidden legacy of cosmic curiosity, the drive to understand where we came from, to decode the message in the ancient sky, does not just satisfy a philosophical urge. It builds better tools for humanity, proving that the search for our cosmic origins actively shapes the future of our world. This ancient light will not shine forever. The cosmic microwave background is slowly fading from view, diluted by the relentless expansion of the cosmos. Each of its photons is stretching, its wavelength growing longer as space itself stretches, a process we call redshift. Think of that primordial afterglow as a note played on a cosmic piano. Over billions of years, that note has been dropping in pitch, becoming a deeper and deeper hum. This cooling and redshifting will continue unabated. In roughly 1 trillion years, a timescale so vast it defies human comprehension, the wavelength of these CMB photons will have stretched so much that they will be larger than the entire observable universe of that far future era. The signal will have effectively vanished into the background noise of spacetime, becoming impossible to detect with any conceivable technology. For any civilization that arises then, the universe will appear profoundly different and far more mysterious. The most fundamental evidence for a hot, dense beginning will be gone, leaving them with a static, eternally cold, and dark sky with no visible clue to its explosive origin. But redshifting is not the only force erasing this cosmic fossil. The universe is constantly creating new light, the ongoing process of star and galaxy formation, and the reionization of hydrogen by stellar radiation is generating a new, diffuse background glow across many wavelengths. This modern cacophony of light from countless stars and galaxies will, over eons, begin to overwhelm the faint, primordial whisper of the CMB. It will be like trying to hear a single, soft voice in a crowded, roaring stadium. This means we are living in a uniquely privileged moment in cosmic history, a narrow window of time where the universe is old enough to be understood, yet young enough that its birth cry is still audible. We exist during a golden age of cosmology, a brief era where this pristine snapshot from the dawn of time is still within our grasp. This knowledge places a subtle urgency on our quest. We are the custodians of this profound knowledge, the first and possibly only generation of beings capable of reading this ultimate story before it fades forever from view. The Big Bang may not have been a true beginning, but a cosmic rebound. This idea challenges the very definition of creation, proposing that our universe is just one chapter in an endless cycle of expansion and contraction. In these cyclic models, the violent birth we call the Big Bang was actually a transition, a great turning of the page from a previous cosmic phase that had collapsed or collided. One of the most compelling versions of this idea is the ekpyrotic universe. It envisions our reality as a three-dimensional membrane or brain floating within a higher dimensional space. In this strange geometry, the Big Bang could have been sparked by a collision between our brain and a neighboring one, a titanic impact that flooded our space with energy and matter, setting off the expansion we see today. This collision would not be a one-time event, but part of a perpetual cosmic dance, a cycle of approach, collision, and rebound that plays out over trillions of years. This fundamentally different origin story leaves a unique fingerprint on the cosmic microwave background. The mechanism that creates the seeds for galaxies is entirely different. Inflation stretches quantum fluctuations from the subatomic to the cosmic scale, resulting in a very specific, nearly uniform pattern of fluctuations across all sizes. But in a cyclic model like the ekpyrotic scenario, the dominant fluctuations are created by the collision itself and the motions of the branes in the higher dimensional bulk. This process tends to suppress the formation of the very largest scale structures. It predicts a distinct lack of power in the largest temperature variations we see in the CMB. Intriguingly, this is exactly what some astronomers argue we see. The large-scale anomalies, like the unexpected quietness of the biggest patches of sky, could be a fossil of this pre-Big Bang physics. It would be the cosmic equivalent of a scar, a permanent reminder that our universe was born from a collision rather than a pure, spontaneous burst. Furthermore, the gravitational waves produced would carry a different signature. The chaotic, high-energy genesis of inflation generates a strong background of primordial gravitational waves, but the smoother, colder collision of branes in the ekpyrotic model would produce a far weaker signal, a whisper instead of a shout. So far, our most precise measurements of the CMB's temperature and polarization patterns align more strongly with the predictions of inflation. The data has placed cyclic models under immense pressure. Yet the search for these alternatives is far from over, driven by the persistent anomalies that inflation struggles to explain. Proving a cyclic universe would be a revolution on par with Copernicus displacing the Earth from the center of the cosmos. It would mean that time itself is without beginning or end, and that our entire cosmic history is just one iteration in an infinite loop of cosmic death and rebirth. The static of the CMB may yet hold the echo of a universe that came before our own. Each instrument in this cosmic orchestra plays a distinct and vital part. The temperature anisotropies form the powerful melody, the main theme of the universe's initial structure. The E-mode polarization provides the rhythm, a steady beat echoing the reionization of the first stars. The faint B-mode polarization is the elusive harmony, the high-pitched whisper of primordial gravitational waves. Gravitational lensing acts as the baseline, the deep, resonant thrum of dark matter bending the light. Spectral distortions are the subtle overtones, the slight warble revealing energetic interactions along the light's path. When played alone, each signal tells a compelling but incomplete story. But when combined, they create a symphony of staggering depth and consistency. This multi-messenger approach allows scientists to perform a cosmic cross-check. A model that fits the temperature data perfectly might struggle to explain the specific pattern of E-modes, or it might predict a lensing signal that does not match what we observe. By demanding that a single theoretical framework, the lambda CDM model, explain every single one of these independent measurements simultaneously, we subject it to the most rigorous test imaginable. This process breaks degeneracies, situations where two different combinations of cosmic ingredients could produce a similar temperature map. For example, a certain pattern of hot and cold spots could be explained by slightly adjusting the amount of dark matter, or by tweaking the initial power from inflation. But when you add the lensing map and the polarization data, the ambiguity vanishes. The combined data forces a unique solution, a single, precise recipe for the cosmos. The result is a coherent and robust narrative. The symphony tells us with incredible certainty that we live in a flat universe born from an early burst of inflation, filled with about 5% ordinary matter, 27% dark matter, and 68% dark energy, and populated by 3 families of light neutrinos. This is the most powerful concordance evidence in all of science. It is not one measurement, but a dozen independent lines of inquiry, all pointing to the same profound conclusion. A self-consistent story of our origins written in the language of physics across the canvas of the sky. This symphony is the unshakable foundation upon which all of modern cosmology is built. Our journey through these ancient whispers reveals a cosmos shaped by invisible hands. The explosive push of inflation, the ghostly pull of dark matter, and the mysterious repulsion of dark energy are not abstract ideas. They are the fundamental architects of reality, their signatures permanently etched into the cosmic microwave background. This afterglow is far more than a static fossil. It is a dynamic data stream, a living message that continues to challenge and refine our deepest understanding of the universe. From the puzzling cold spot to the unsettling axis of evil, these anomalies are not mere glitches. They are potential signposts pointing toward physics we have yet to imagine, cracks in our standard model that may one day swing open a door to a grander theory. At the same time, the breathtaking precision of the CMB's power spectrum provides the unshakable foundation for modern cosmology, giving us a complete and coherent census of the cosmos. This ancient light is our most powerful portal to the beginning of everything. As next-generation telescopes like the Simons Observatory and CMB S4 come online, we stand at the brink of profound new discoveries. We are poised to potentially capture the faint swirl of primordial gravitational waves, a direct echo from the universe's first instant. We might finally uncover indirect evidence for a multiverse or pinpoint the nature of dark energy. The story written in this ancient light is far from complete. Its final chapters promise to hold surprises for generations of scientists to come. Let this exploration of the cosmos ignite your own sense of wonder. We would love to hear which of these unseen forces captures your imagination the most. Share your thoughts in the comments and subscribe to continue this incredible journey of discovery together.